Hello everyone. We discussed the Carnot cycle in previous videos, and we discussed also the reverse Carnot cycle. So we discussed what processes are involved, and the Carnot cycle have the highest efficiency that a heat engine or a refrigerator can have, operating between two, basically one source at temperature TH and one sink at temperature TL. Now, Carnot came up with the principle based on the second laws of thermodynamics, and he mentioned that the efficiency of which are famous basically by the name of Carnot principles. And what he's saying is that if you have, for example, heat engines operating between the same high temperature source and low temperature sinks, then if you have an irreversible heat engine, then the efficiency of the irreversible heat engine is less than the efficiency of the reversible heat engine. And any two heat engines that are reversible operating between the same source and sink temperatures will have the same efficiency. So that's called the Carnot principle, and that's based on the second law of thermodynamics. It can be proved. The proof is inside your book. You can go ahead and read that part. We're gonna skip the proof of that, but these are called the Carnot principle. So next we're gonna talk about the thermodynamic temperature scale. I think we already talked about it in chapter 1. And remember that the thermodynamic temperature scale is independent of the type of materials that you're measuring the temperature, and in SI unit, Kelvin is the thermodynamic temperature scale, and in English unit, Rankine is the temperature scale, which is thermodynamic scale basically. So it can be proved for the Carnot cycles that the ratio of the heat transfer from a high temperature reservoir to your system over the ratio of the heat that your system loses in a reversible process is equal to the ratio of their temperatures. This is a very important equation that can be applied for the reversible heat engines and refrigeration processes. Look at this REV that is written there. That means reversible. And these temperature scales that you use in this equation, they should be thermodynamic temperature scales. So these are in Kelvin. So the ratio of the heat transfer from high temperature source to your system over the ratio of the heat transferred between your system and the low temperature sink is equal to the temperature of your high temperature reservoir over the temperature of your sink. So you have to use the Kelvin temperature, and if you have degree centigrade temperature, you have to convert it to Kelvin by using this equation. Alright, so now remember we defined the efficiency of any heat engine by mentioning that eta, the efficiency is 1 minus QL over QH. Now if you have a Carnot cycle, you can substitute. Remember this ratio in Carnot cycle is TL over TH. So you can substitute it, and for Carnot cycle, the efficiency of a reversible Carnot cycle is 1 minus TL over TH, and that's the maximum efficiency that you can get from any heat engine. So if you have basically a heat engine operating between a high temperature source and a low temperature sink, if it's irreversible, that efficiency that you receive from that irreversible is always less than this. If you have a reversible operating between those two temperatures, then that's equal to any basically reversible other heat engines operating between the same temperatures. And if you have an efficiency higher than the efficiency of this reversible process, then that's impossible heat engine. You cannot have such a heat engine working. An example of that is, for example, let's say you have this Carnot cycle. You are receiving 500 kilojoules, and your high temperature reservoir is 652, and you're losing QL to the low temperature reservoir. which is at 30 degrees Celsius. The goal is to calculate the efficiency of this Carnot cycle, as well as calculating how much heat is being lost to the low temperature reservoir. So remember Carnot cycle, again, you can calculate the efficiency by using this equation, just by using the temperatures of your high temperature and low temperature reservoir. The only thing that you need to consider is that you need to convert these degrees Celsius values to Kelvin and then put it into the equation. That's 67.2%. So 67.2% is the maximum efficiency for any heat engine operating between this high temperature reservoir and low temperature reservoir. Okay, now how much heat is being lost? Remember, there is we had this equation again, QH over QL is equal to for a reversible again process is equal to TH over TL. So you have TH, you have TL, you have QH given to you, so you can calculate QL from this equation, and that's 164. Again, make sure you use Kelvin in these equations. Okay, so that's 164 kilojoules being lost to low temperature source. Next, we want to talk about the quality of energy by just doing an example. So if you look at here, you have a heat engine operating between two reservoirs, one at TH, one at TL, and assume that you keep the low temperature reservoir temperature constant, okay, at 303 and 3 Kelvin, and you start the high temperature at 925, and you start to decrease that high temperature reservoir temperature from 925 to 350, and look at how much the efficiency of your heat engine would change. Now it's easy to calculate, right? The efficiency of a reversible process Carnot cycle is calculated by this equation. The only thing, the parameter that is changing is TH. TL stays constant, that's what we assumed. TH is changing from 925 to 350, and you can see the efficiency is changing from 67.2% to 13% when the temperature of the high temperature reservoir reaches to 350 Kelvin. So what it means is that the efficiency of your heat engine is dropping if your high temperature reservoir is dropping. What it means is that the quality of energy at high temperature is higher because it has higher efficiency, and the quality of energy is lower when your high temperature reservoir drops to 350. So the higher the temperature, the higher the quality of the energy is, and the lower the temperature, the lower the quality of the energy is, because you will have less efficiency in a reversible process. So energy have a quality, and that's a conclusion from the second law of thermodynamics. Now you can calculate also the maximum efficiency for refrigerators and heat pumps. Remember, we defined the coefficient of performance, and it was defined by this for any type of heat pump and refrigerators. Now if you have a Carnot cycle, remember again, QH over QL for a reversible process is TH over TL, and you can substitute that here, and you can get, so this is for refrigeration, this is for heat pump, and then if you substitute this relationship, you get these two equations for coefficient of performance of Carnot refrigerator or heat pumps. Now again, you have the same conclusions if you have two reversible heat engine refrigerators or heat pumps operating between the same temperatures, then they have the same efficiency. The coefficient of performance of a irreversible refrigerator is less than a reversible one, and an impossible refrigerator is a refrigerator that does have a coefficient of performance higher than the reversible refrigerator. And this is also written in this slide, and we can do a quick example on that. So assume that you have a heat pump operating and the outside temperature is -5 degrees Celsius. The house is being to keep constant to be kept at constant temperature of 21 degrees Celsius, and the goal is to calculate the coefficient of performance of the heat pump. We're losing 135,000 kilojoule per hour of heat from the house, right? So if our heat pump is operating at with the Carnot cycle. Let's calculate the coefficient of performance. It's 1 over 1 minus TL over TH. Make sure you convert these numbers to Kelvin. So once you convert it to Kelvin and then put the numbers in, it's 11%, very low, right? And that's for the reversible process, right? And if you have any reversible, it's lower than this for sure. And to calculate how much work you need to keep the heat pump working, then you have your QH value, which is 37.5 kilowatt, just by simply converting this to kilojoules per hour per second, right? So you have to divide this number by 3600, so 135,000 divided 3600, then this makes it 37.5 kilowatt, and that's your QH divided by coefficient of performance. We had this equation in the heat pump, you can check it out. It's 11%, so sorry, not percentage. Sorry, I miss. I thought this is percentage, right? So no, this is a number, just 11. This is coefficient of performance. I just get confused. This is not efficiency. This is coefficient of performance, which could be more than 1. And QH over coefficient of performance, then you get 3.32 kilowatt work needed to be input. So with that, this chapter is finished, and please let me know if you have any questions.